In this exercise, we look at some sets and determine whether they're open, closed, neither, or both. Got some relevant definitions and theorems here. If S is a subset of the reals, then if the boundary of S is entirely contained in S, then the set is closed. If the boundary of S is entirely contained in its complement, then S is open. Here's a very useful theorem, 347b. A set S is closed if and only if the complement is open. And paired with theorem 3410a becomes very powerful. The union of any collection of open sets is open. So let's apply these to some sets. Set A is 1 over n such that n is an element of the natural numbers. And set B is the natural numbers themselves. Both of these are very similar. In each of these sets, every point is a boundary point. And the reason for that is any neighborhood of any point in these sets contains points both in the set and in its complement. Since every point is a boundary point, by definition, the boundary is contained in the set. Therefore, both of these sets are closed. And clearly, the boundary is not contained in the complement. Therefore, both of these sets are not open. Another way to think about this is to look at the complements. So the complement is comprised of sets like these, such that n is an element of the natural numbers. So if you take the infinite union of either of these by theorem 3410a, you get an open set. And hence, the complement is open and the sets are closed. Now part C, we've got the rational numbers. The boundary of the rational numbers is all of the real numbers. And the reason for that is, if you take the neighborhood of any real number, any interval contains both rational and irrational numbers. So you've got elements both in the set and out of the set, and therefore every member of the reals is a boundary of the rationals. So the boundary is clearly not contained in the rationals because we have irrational numbers in there. Similarly, the boundary is not contained in its complement because we have rational numbers in there. So this set is neither open nor closed. In part D, we have the infinite intersection of this interval between 0 and 1 over n. When you take the infinite intersection, there's nothing in it. You have the empty set. The boundary of the empty set is the empty set. So clearly, the empty set contains the boundary. The complement of the empty set is the reals, which contains the empty set. So the boundary is contained in this complement as well. Therefore, this set is both open and closed. Part E, we have x such that x minus 5, absolute value, is less than or equal to 1/2. And that is simply the closed interval between 9/2 and 11/2. Now the boundary of this set is the 2 points 9/2 and 11/2. And that's clearly contained inside that closed interval. Therefore, that set is closed. The boundary, however, is not contained in the complement of that set, so it's not open.